start. So welcome to this afternoon's lectures. There's going to be 4 topics this afternoon. First, I'm going to talk about systems with coupling. So we're adding connections between parts, so add some nonlinearities. We started with systems with independent parts. Now there's dependencies and couplings. And then we'll talk about overloading and multiple levels. But there will also be a part of the lecture on the theory of ΔQSD given by Hossein Hayri. And I will talk about an algorithm design example, the Cardano Shelley block diffusion, where it's actually using ΔQSD not just to diagnose, but to design the system. Okay, so the first thing I want to talk about is coupling. So this is not as well developed as the thing this morning. So I'm mostly going to give you examples, some examples of how couplings are how it is modeled, okay, and dependencies. So I will give you an example called iterative query. Okay, so in lesson 2, we had systems with independent components, where the semantics of the outcome diagram basically is compositional. Okay, we can decompose it into parts, compute the delta Qs, and then combine them. That's the starting point. But in fact, real systems are not so simple. They will have nonlinearity. And the first kind of nonlinearity I want to talk about is coupling. For example, if 2 components are running on the same CPU, then there's a coupling between them that can cause their behavior to change in a nonlinear way. Shared resources, for example. And then the final lesson, we'll talk about overload, when systems are overloaded. So the delta Q of a component, so it's a CDF, but this is not a constant function. This depends on time, and it depends on the offered load of the system. So if the load increases and beyond the capacity that the system was designed for, then the delta Q will change a lot, okay? And so we're going to study that. Temporary overload. But if this happens too often, if the overload situation happens too often, then you need to do something more. You need to actually look at the system at different time scales and levels, and that's permanent overload, okay? Shared resources. So the delta Q is simple if the components are independent, but we have shared resources. So the first thing, so the way to do that, is the delta Qs, the computation, we have seen how to combine them. But if you have shared resources, this adds, sorry, can you stop the recording a sec? I don't know why. So real systems have shared resources, and a shared resources is a part of the system that can potentially, so a resource is something that can be shared. And the way to model that, to add that to our model, is to add variables and equations to the model. And the computing of the delta Q is then no longer so simple. It's no longer simple compositional computation of the delta Qs, but it actually requires a more general kind of a solver. So it depends on the equations that you add. It could be a numeric solver or a symbolic solver. So that's the way to do that. So that is not a real showstopper, but it does mean that this tool requires more computation. Okay, so let me first talk about different kinds of resources. What are resources? So there are different kinds of resources that have or that need different kinds of modeling. So it's important to understand how they work. And there's 2 properties of resources, 2 axes in fact. So that gives 4 possibilities. So first of all, a resource can be ephemeral or not, and a resource can be a threshold resource or not. So an ephemeral resource is a resource is available at a particular time instant, and if you don't use it at that instant, you lose it, okay? So for example, power coming out of an outlet, that power is distributed at the instant that you use it, and if you don't use it at that instant, that power is gone. There may be new power later, but that power is then gone, okay? And a threshold resources is that if you use more and more of it, if you reach a particular threshold, then the system basically collapses and fails. So bottom in the technical sense. So if you, again, in power outlet, if I extract more and more power, if I reach a certain level, that will cause a circuit breaker to trip and the amount of power will drop to 0. Okay, so that's a threshold resource. Okay, if there is still some functionality, it's not a threshold source. So it really has to drop to 0. So all 4 kinds of resource exist and they cause different kinds of modeling. So a network connection is ephemeral, but not threshold. So the network communication exists at a particular time instant. But if you overuse it, it doesn't drop to 0. It just reduces. If there's more and more congestion, performance goes down, but it doesn't suddenly drop to 0. So it's not a threshold. And similar for a shared CPU. When too many processes are using the same CPU, so as long as there's enough memory, then they will all keep going at reduced speed, but the performance will not drop to 0. So they're not threshold, but it is ephemeral because the CPU power is available at a particular instant. And an instant later, you don't know whether the clock is still going to be running. And then you also have ephemeral threshold resource, for example, the working set of a process. So a process requires a working set of random access memory in order to do its stuff, and the other pages that it doesn't need are stored on disk, okay, and they're swapped in and out. But if the size of working set exceeds the maximum random access memory available, the performance drops incredibly a lot and essentially goes to 0. Okay, so this is a phenomenon called thrashing. The same for the mains electricity as an outlet, as I explained. And then there's other ones that are not ephemeral. Not ephemeral tend to be more things like batteries, where the resource is stored over a time and you can use it over time. So a battery is a threshold resource. When the battery runs out, it gets 0. But if you have a tidal energy generator with battery storage, it keeps being replenished. So it never actually goes to 0. It can go down and down, but not to 0. So those are the different kinds of resources. Now I'm basically going to give you some examples and the kinds of equations that you need to solve. So first example is congestion. So we have 2 sources of load, of packets coming in. We have here this router, and let's say there's 1 output network. So all the packets coming in through the MX packets and the MY both have to go through the router. And the little number A here is denoting the offered load. So this would be the number of packets per unit of time. So the amount of load actually going into the router is the sum of AX plus AY, okay? So the delta Q of this router will typically not be a constant function of delay, but it is also a function of load. So we will see later how that works, okay? How temporary overload, for example, can cause delta Q to get worse. But here we can just say it gets worse, okay? So typically you would have buffer overflow and message gets dropped, okay? And there's congestion. So if you have a certain kinds of models for the router, you can have this kind of behavior, buffer overflow, message drop, if the total load is beyond a certain threshold, okay? There's a question?
I was going to point out that, the model of effectively the delta Q of the router, the queuing model, a lot of it's based on arrival patterns, things like this, the context sensitivity stuff. There's a richness inside there that you can refine, but actually you can also start off with some simple models of your queuing system.
Right.
To get you boundaries on looking.
Right. So that's something, yeah. So what Neil is saying is that there's many different kinds of models here of the router. So we will look at one simple model, which is called an MM1K queue. And in this model already gives actually reasonable intuition on how components work. But as Neil says, the real life, it's much richer than that. And it might not, this model might not be enough. But in fact, this MM1K model, it'll be enough for us to show the essential aspects of temporary overload, for example. Okay, so I'm not going to go farther in this example, just to say that you have these two variables, AX and AY are determined by other parts of the system. So this is a part of a bigger system diagram, an outcome diagram. And so that you have this extra equation, A equals AX plus AY, and these three variables then would occur in the different parts of the system. So that means it's not just enough to compositionally combine the delta Qs, you actually also have this equation that comes with them, okay? So you have to find a solution to that. And you can have all kinds of problems with that, divergence, convergence, and so on. So here's a second example, load balancing. So again, it's something related to load. So we have the load coming in A, we split it. So P and Q are fractions of the load, less than 1. They go to 2 servers. So each of these server 1 and 2 will treat a fraction less load than A. So Q1 of P times A, Q2 P times A. So the total delta Q here is actually the weighted sum, okay? It depends on, it's a probabilistic choice. So each time a task comes in, it either goes to the top server or to the bottom server according to the probabilistic choice, okay? So you have this extra equation here that's added. And then, again, using the model of the MM1KQ we introduced later, you can see that if you don't want congestion, if you don't want these servers to be overloaded, that P times A and Q times A have to be less than approximately 0.8. So the normalized offered load is 1, which is the number of incoming packets is equal to the average rate at which they can be handled. So this is a simple example that you can, of course, extend with priorities and so on. So again, you get an additional equation and you need some kind of a solver. So these are 2 simple examples. Here's a third example, a shared CPU. So we have 2 components that can be anywhere in the system, and they're running on the same core, okay, same processor core. And the C1 is the fraction of the processing power that they're using as a function of time. And the sum of these 2 is equal to 100%. So we have these 2 extra variables and this extra equation. So then again, you have to compute what is the equilibrium situation of your system. So again, you need to have a solver, extra argument C1 and C2, and an equation. So again, this is a fairly simple constraint. Let me go now and show you an example with a more complicated constraint. Yeah?
The CPU example brought into mind. It's all about queuing discipline. And when you do processor sharing or first come, first serve, whatever makes the difference, does this support any notion of queuing? Does it need to?
Right, so the first thing, if there is a feasible schedule, then there is deadline first. Right? So the first question is there yes? Right. Now you can approximate the feasible schedule by actually do this sort of literally say there's a box and you pour the liquid in and balance out to see if I had perfect scheduling, but actually better. So that's an infeasibility. Secondly, we're working on the normal issues of processor scheduling, quantization, but each one of those steps costs, right? So we're building the cost of doing that. How can we reason about the feasibility of sharing the resources like that? Then in the real world, we've done things using the problem with processors is they've been like entirely like caching, cache solution problems. You know, again, this is not necessarily finding feasibility questions, whether, you know, where does the solution space look like? Because from a commercial perspective, we've done that and then already done it in a lab afterwards. But if you were to have tried to have done it in a physical lab, as a technical experiment, that's just the lab space. The research space was crazy.
Yeah.
So yeah, the answer is yes, we can do various models. But you've got to, again,
but there's some diminishing returns at some point. So cache, for example, the real behavior of the cache depends on the detailed sharing behavior of your application. Okay? So unless we want to model the actual application, you can only go so far in these models. So you have to be careful.
Can I just sort of carry on that? Well, actually, it depends on, there are constraints on the behavior of the application. Knowing what those constraints are, we are now in a position of talking to people who write the applications generally. All right. Now, in the telecoms industry, getting this right is a multi-billion-dollar solution. And basically, we've worked out what the constraints have to be on certain types of packet handling. Question actually turns out electrical engineers put the software. So, this is our constraints, right? Again, like this is the cycle of planning, doing this stuff, right? So
yeah. So there's a lot of
both ways.
Yeah. But it's also richness. Are you worried about average performance? Or are you worried about worst case performance? So a typical laptop is very bad for worst case, huh? Because everything is optimized for the average case in a laptop with caching all over the place. But this is the hook into the ΔQSD. But I want to give a more complicated example before going into an actual equation that we want to solve. So here we have an interesting nonlinear sharing. Two carriers, C1, C2, are sharing a cell tower. Okay, so they will both communicate with that single tower, and each carrier contractually is guaranteed at least 50% of the tower's capacity. And the joker is each is allowed to use the capacity at any moment in time that is unused by the other. Okay, so for example, if carrier 1 is using 30% of the capacity and carrier 2 is using 60%, so that's allowed, the total is 90%. Now, if carrier 1 suddenly decides to take its 50% share, which has the right to do that, carrier 2 will immediately drop to 50%. There may be also some packets and transits will be lost. So formalizing this kind of a constraint is more complicated, and it's a very discrete kind of a constraint that requires a more sophisticated solver. So for example, here's one possible formalization. So each carrier requests loads, so AC1 and AC2, that are between 0 and 1. The shared tower grants loads BC1 and BC2, and the total load tower of the load is the sum. And now we have the constraints. If the carrier C1 is requesting less than 50%, then it gets everything. Okay, if it's greater than 50, if C2 at the same time is greater than 50%, then it gets the minimum of AC2 and 1 minus AC1. So so if AC1 is not using its full share, okay, it gets that, and C2 is actually allowed to get the leftover share, okay? And the same thing in the other direction. And if both are greater than 50%, then we say they both get 50%. So this is a dynamic system, okay, which is all functions of time. So the solver for this is more complex, okay? But at least we have the equations.
Is this a real thing?
The sharing,
Share the towers?
this is a real thing, yeah.
The thing that they share is the backwards.
Oh, okay.
Right. So actually, what happens to happen is they each have their own radios on the tower, but they have a shared backward.
Okay.
That's the constraint.
And basically, what Peter is positing is
This is just my possible formalization, because none of this really exists.
The problem is it doesn't exist. And actually what happens is the dynamic behavior described there is that basically you can go for 30%, 60%. And the delay in the other line goes to both. And then actually, this is an example where a whole cell tower goes down.
So you may not want to give a carrier more than its 50% if the other one is unused.
The economics of asset sharing was based on sharing the backward. So there's an economic model that says we share, practically they can't, but they don't have the mechanisms to smooth the sharing out, so that basically the rates of change are managed, right? So again, it's showing a lack of a control mechanism. We can talk about it.
At least we can talk about it.
Because
yeah.
Otherwise, the net heads basically say, well, TCP solves this.
Sure it does.
Sure. So this is another example where if you had thought about how about sharing backward cell tower? Well, let's do some performance analysis and see what the implications are.
As opposed to the.
And then you might conclude that either economically it's not a good idea, or we need some more nuanced way of doing it, rather than just allowing a kind of best effort free for all, to treat the traffic with some liberties
Right.
that guarantee you 50% improvement, but tell you nothing about the time.
So actually, there was consolidation with the UK study the market based around resource sharing, which worked. Which basically they formed companies that need assets because they share backholes.
The joint ventures were created.
Joint ventures
Oh,
were
wow.
created,
Like
resources
oil exploration.
And then what happened is the emergent property of this started to hit them. They all backed out. They wasted millions.
Wow. But they could have
They
done
could
it
have
more
gone
effectively.
Yes.
Right.
Okay. So again, this is, we talked about the performance engineering is there to be had, but because they can't get their head around how to perform a question, or if that question should be asked, they just go ahead and they believe in the network fairy dust. That's all.
The invisible hand theory. The invisible hand of the network.
TCP will solve everything. Yes. And even Vint says it doesn't.
Ooh, even Vint. Ooh, a divine revelation has descended from heaven.
You know, we've had discussions. Right, but the point is, they believe that somehow.
Yeah.
TCP and Vint server and Van Jacobson, somehow they're magic solving.
Somehow they have foreseen it all.
No, basically.
It's been the first one to say that if you use protocol,
Yeah.
you need to use the design properly.
Right. He's the most reasonable of all those guys. Yeah.
Nobody designed this thing to be used by billions of people.
Yeah. It's amazing how well it's held up, given the.
Only by vast efforts globally. I mean, the cost of maintaining the internet is actually something that society bears.
There's a famous, there's this famous XCCD comic about showing the whole internet stack, and then there's a small thing, little piece of software maintained by a guy in Alabama, basically holding up the whole internet. Okay, so okay. So now I want to show you a more detailed example, an iterative query example to how this kind of solution could actually work. Okay, so here we have a user sitting in front of his laptop server, and the user sees something, thinks and clicks, and then the system reacts, and then the user sees something and clicks again. Okay, so the user sends a query, which sends a response back, and then the user sends another query. So you have this iterative system. Okay, so this is actually a very common model of human-computer interaction on the web. Okay, software doing iterative queries to a database, many kind of software which reacts is behaving in this way. So question, what is the delta Q for this system? Okay, so we're going to look at that. First of all, the outcome diagram. So it's a cyclic graph here. But if you look at the actual outcomes, okay, so an outcome is a pair of a start event and a stop event. So we have query, RQN and RN, that's an outcome. But also RN, QN plus 1, that's another outcome, which is causally dependent on the previous one. So there's basically an unbounded sequence of causally dependent outcomes, okay? So that's interesting. Let's write down some equations for that, okay? So we will do that in this case. So I'll make some simplifying assumptions, okay? We'll say the server's delta Q is a function of load, and we will make a simplifying assumption. And the total and the load, we will assume that delta QS is also some constant, the thinking time of the user. And the load is the function of the total delay. So the total delay is the sum of the both. That's one iteration. So the load A is the expected rate of queries. So if you look at the density of this load, so the derivative, so the density of this delta Q here is basically how much load there is in every time unit. So per time unit, and we make the integral over from 0 to infinity, gives us the total load A, okay? So this is a recursive equation. So let's see how to solve it. So I make some assumptions here. So first of all, the delta Q of the server, if we use the MM1KQ, which I haven't introduced yet, but at very low loads, it has the following approximation. So the load A, when it gets very close to 0, this number gets smaller, and the service time is a constant, okay? So that's the delta QS. The user time, we'll assume the user always thinks the same number of seconds. So we take the convolution of these two, but since this is a step function, it's just shifting, and then we make the derivative, this gives this density. So now we can actually, you can see this function here, huh? What it is here. So we have, it starts at d plus as over 1 minus a, and it's a width of s. And we solve this integral equation, which I have done. And this solution is very interesting. A is 1 over s here in the natural log of this function, but there's this d over s ratio, which is very important here. So d over s is the user over the server time. Okay, so let me graph this and show you what it gives. So this actually gives some very interesting results. So here we have the load A going from 0 to 1. And so this 45-degree line is where the function is equal to A. And these curved lines here are the function 1 over s of the natural log, depending on the ratio of d over s, okay? So if d is very high and s is very low, then we have a slow user, okay? And then you can see here the intersection is 0.18. So basically what that means is that the user is the one directing it, it's pacing it at the pace of the user. Whereas if d is 1 and s is 1, then you get a higher performance, okay, less the user. But if the d is 0 and s is 1, then the user immediately clicks, tuck, 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 but you still have the server time here. So then you get 0.57, okay? So with this graph, you can actually see how the load, the solution changes depending on the ratio of the server, of the user time and the server time.
Just getting to control the camera so we can see you better. Yeah.
But then I moved too quickly.
Then you moved too quickly. Never mind.
That's okay.
That's okay.
So this is just an example, and notice this example depends on several approximations, huh? So this is just so that I can actually work it out in a closed form, but still it gives results that are intuitively correct, huh? Because these approximations typically will hold for low loads. If you look here, but this left approximation in the top left is really only true for the MM1KQ at low load. Okay, so MM1KQ is also already an approximation, and there we're approximating this exponential function, so this negative exponential here by a uniform. Okay, we're assuming there's no infinite tail. So all of that is an approximation, but still it gives. It's interesting, huh? So this is the kind of thing the solver has to do. Huh? It has to. Normally, this would be numerical solutions. Okay, so that's the example, and it's not. You can actually do very nice iterative solutions. So if you start with the given load, you can actually converges pretty quickly. Yeah, you start with A, you find the function, and if you go directly to the 45-degree line, then you can immediately go to the next function. Huh? So you can see that it actually converges. This recursive equation converges pretty quickly. Huh? Okay, so that's most of what I want to say for this part. Then you can do variations like back-to-back servers, where you have two servers kind of fighting each other, each with its own service time, okay? Or two collaborating human teams, computing things and sending things back and forth to each other, okay? So interesting points are what happens when the two service times are different. If S1 is different from S2, so the slow server is kind of controlling it. So this kind of thing is something that you can compute. So this gives an example of the kind of solving you need to do. Okay, so that's all I want to say about sharing. So now, Hossein, you can give a talk on some theory. So there's a lot of actually And Hossein has been the main driver, a lot of theoretical foundations of this work. So you're going to give an introduction to that, huh, Hossein?
So, would you like to maybe pause that? Yeah, sure. Until I said something.
Thank you. So, in the name of God, the compassionate and merciful, this is I'm going to show you a bit of the theory that we have been developing. I need to be very frank on it that I'm a programming languages person, and I'm only doing the formalization of what comes from P and Soul, and the credit is actually theirs, it's not mine. So now, so back to this big picture of the example that I'm going to use as my driving, that my Peter just told us about a few sessions ago. We are going to deal with a cache that once a read comes, will either have a hit or a miss. And if it's a hit, it will return what it has. Or if it is a miss, then it will go through a network to a main memory somewhere remote, look it up, and then return it back again through the network, and all of that is timed out. So if this is not timely enough, we will return, but we will return with a failure rather than a success. Now, we have already seen a lot of a few outcome diagrams, so I'm not going to put a lot of time in explaining all of the details, but just to show you enough. Now, considering the only part which states hit or miss, this is how we present it. So we have a probabilistic choice between two outcomes. The cache hit, which we show using a C dash hit, and the cache miss, which we show by C dash miss. There is a likelihood of 95% for a hit and a likelihood of 5% miss. This is how we show it. Now, a few things. In my slides, outcomes are these amber circles. A bit of a difference between what Peter has shown. Not really fundamental, but just to make sure that no one is being confused because of that. Now, something again that I have to remind is that the mind shift that we talked about. I think it wasn't in the recording, but the mind shift is to be noticed right here. That outcomes are not any of the like they're not system states, they're not processes, they're not subsystems, they're not classes or objects. Outcomes are something else. I'd like to think of them apart from the fact that they have observable beginnings and ends. What the system gains by performing one of its tasks. Now, sign for the probabilistic choice is this kind of arrow that you see here, which also shows up here in the diagram. Now, but what happens when you have a miss? You have to go to the main memory. So that's our sequential composition here at the bottom in this branch. Right now, on my slides, there is this left to right causality convention. So if something is to the right of something else, and there is a line between them, it means that that one is causally dependent to the one to the left of it. And then, so when you go to the main memory, there's always this possibility of having some failure. There is a error correction mechanism that we take for granted, and there are weights. So 1 in every 10 to the power of 16. There is the chance of the main memory lookup also failing. And of course, you go through a network here, and back again, okay. So we would like to take a closer look to this proportion of it. Here it is. So this is what we had before. Now we want to go through the network also back and forth, the other direction, of course, and we would like it to be timed out. Now notice this new operator here, the any to finish or first to finish, formerly called, with the sign of existential quantification. Now, the thing is that, okay, so this is diagrams that we have thus far seen diagrams, but there is the reason the way we put that into mathematics is that there are also expressions that go with each of these. So for example, this going from the very smallest of our proportions, provided that you want to all own top, the expression that you get is that this is a probabilistic choice between looking up things from the main memory and this sign here, the bottom sign, which is for failure, right?
Is this intended to be some kind of like process?
Well, it's very close. It's very close, but it's not that because of the changes because of the differences that you get in the mindset. You know, but it's very much induced by that.
You end up with an algebra and rewrite it.
Okay.
Yes.
Yeah.
But indeed, it's an algebra.
Yeah.
Rewrite that.
Yeah. Indeed, sir. Indeed, sir. Now then you add the network back and forth, and the diagram above you've seen. The new thing here is this sign, which is for our sequential compositions, right? And that gives you a larger expression. You can even put the network in, put the timeout in, and then you get the first to finish. There's the new sign here, the new operator in the algebra is this, for any to finish or for the first to finish. And the full picture gets this larger expression, which has nothing new in it. I'm not going to delve into more details at this point. And then, so once you've got that, once you have a piece of mathematics that describes your outcome, then you can do interesting things about it. And in particular, I'm going to talk about timeliness and how that algebra relates to time. So before I do that, I would like to walk you through the definition of what we mean by timeliness. I'm going to read that box for you. Timeliness is delivering results within the required time bounds sufficiently enough. Or sufficiently often. I'm not very good at reading that. Right. And there's a piece of picture that you have seen before in Peter's slides. You know, this is kind of our way of depicting that. You will see more of this in the later slides. What is to notice is that there are two plots here. There is the green one. What's the name of this color? There's this green one, and then there's this black one, and the black one is to the left and above. And so long as that is the case, with the mathematics that I'm going to show, things are good, right?
Does the less than equal to the imply the distribution is one?
Yes, that's the meaning.
Indeed, so there is a partial order.
Yes.
Which when you put, you get exactly what you
So
say.
if I nick the corner of those things,
Then
That's when the fun starts.
yeah,
Right.
Okay.
Well, actually, we have stories about how to have a methodology for talking about those nicks.
Okay.
And we'll get back to that on the last lecture.
Right.
There will be a nick that you will see.
yeah, and there is even support for that in our Jupyter notebook. So
We call it slazzard. We introduce slazzard.
Yes.
Slazzard.
Yeah.
Very
Yeah, thank you. So, okay, now Peter introduced us to the important thing here, which is the quality attenuation. And the other Peter gave us the reason behind it, the reasoning behind it, the philosophy. The philosophy is that you want to measure how far away you are from perfection. And that's with the concept of delta Qs, with the quality attenuation, you measure the delay and the failure together in just one item. We usually represent that as cumulative distributed functions, distribution functions, or sometimes as the probability distribution functions. And one of the major contributions of ΔQSD to the world of performance engineering is the idea of using improper random variables for that representation, because with that, so improper, for those of us who don't know what an improper random variable is, it's the random variable that will not necessarily make it to 1 if you integrate over them from minus infinity to plus infinity. And so what is really important is that there is the possibility for an IRV, an improper random variable, to have this failure, right? It can show that amount that is away from 1. Now, so a bit of a squiggly, just so you know that we are serious. So if you give me an outcome expression, and if you can tell me what the delta Qs for the individual expressions are, I can tell you using this large store of squigglies what the total delta Q of the expression is. A bit of a difference between this and Peter's lectures. This is the sign for convolution. We were told in one of our papers that we should use this because the other one is used for other purposes. And I would like to point out that Peter put a lot of effort into explaining the case for sequential composition, which is the one here. So that's the convolution story. He has a good number of slides on it. I'm not going to delve into that. I would like to pick up on the probabilistic choice. So this part of the formula says, if you have a probabilistic choice between 2 outcomes, O and O prime, with the weight of M going to that way, O happening, or O performing, and M prime, O prime happening or performing, then you essentially get in order to kind of compositionally work out the delta Q for the expression, the total expression, all you need to do is a weighted sum. Right? You take the delta Q of O, you proportionate that with its weight, you add that to the same for O prime. Right? I'll let that sink in. Okay. Are we good? Now, the other one that Peter also put some effort on is the any to finish, or the first to finish. Now, the gist of this is that this is the probability of either event taking place. Right? It's the usual union of 2 things minus the intersection of them. So you add the 2 because either of them can happen, but what if both of them happen? Right? You want to discard that part. Would you?
So it's implemented by multiplying the probability of the two. So each of these is a given probability at a certain time. So each time we multiply the probability.
Like two CDFs we would multiply.
We multiply them
Point-wise, yes.
Oh, but point-wise multiplication doesn't CDF. Yeah.
Correct, correct, yeah.
But that, I mean, that comes out of the probability.
I can imagine.
Yeah, I'm lazy. We don't get other people.
Right. So I promised to show you how this works for the cache example. So the idea is that if you give me a delta Q for each of the individual outcomes in the cache example, which is this, and we call that a basic assignment, right? Then I can tell you that the observed delta Q of the cache example as a whole is this, where the memory itself can be further drilled down to this, right? So that's how you use the squigglies that I showed to compositionally calculate the overall delta Q. I have the habit of counting the number of yawns I get in my presentations. So I've got one now. Yes. Yep. Now, so okay. Now we've seen the delta Q that will be observed in the formulae, right? Now the question is, what good is that? Right? I would like to remind you that we said the timeliness is about performing better, right? In sufficiently often, right? So how do we quantize that? There is this thing which we call the better than diagram, which is the better than what? What is
Well,
yeah, just
expresses
yeah.
the delivered delta is better than.
Right. Yeah. So I would like to now speak to you about this blue one, which is the one that is required, right? So the delta Q that is required. So suppose that the cache is to deliver 50% within up to 5 milliseconds, 95% within 10, 97 within 15, and 3% of the queries are allowed to fail, right? Never come back within a given range of time, right? Now, if that is the case, then plotting it would give us something like this blue one that you see, right? Now, if our observed one is this, then we're good. We've quantized it. That's the important thing. And now the count goes up to 2. Okay. Now, I have seen you, I have shown you the algebraic description of things, but I haven't shown you where that makes it to the algebra that they teach us in universities, right? You get an algebraic description of something, you want to do something useful. Yeah, let's see some of them. So, right, let's say that our focus is at the moment on this part of the diagram. Notice that there is no network involved. The only thing here is that we have a lookup in the main which can fail, right? Now the expression for that is this, right? It's a probabilistic choice of 90% hit and 5% miss, followed by a lookup to the main, which itself can fail with the rate of 1 to the 10 to the power of 16. Now, I am now going to apply a series of algebraic tricks that are justified in our paper using the algebraic laws that we have proved, and get something important out. So this expression to the top, I can rewrite to the one level below. Notice that the parentheses have changed position now, right? These ones, I'm kind of pushing the parentheses to the left, right? I'm kind of redistributing the parentheses, and then I'm taking this bottom sign out here to the top level, and using the formula that we have proved, we can then, the important lessons here, we can then work out this failure rate Q to be this number with 17 nines. So you can compare that with the 9 nines of Ericsson that they show off all the time back. 70 nines. Right? Now, what that is saying is that were us to deliver a product that has a higher success rate than this design would have failed. Right? And we gained that piece of information by, those 3 lines you can do back of that. Right? That's the important lesson to me. This is that we gained that knowledge so quickly. Right? This is the where ΔQSD particularly shines. So we have colleagues in IOG that sometimes take time of several months, is it, to produce results that we produce as quickly as this. Not to say, though, that they are not good. I'm going to get back to that, but the question to ask at this point is that what if we wanted that system with a better success rate than that, and we had implemented the current architecture? What would have happened? Just we'll simply throw in more hardware to work. Should we do re-architecture? And the conclusion that I'd like to draw out of all that is that that's such a waste of time and energy and all resources. We can prevent that very quickly. Right? Now, it's important to notice that this is not to say that we think that ΔQSD is the king of all ways to verify things. We never actually. The matter is, how quickly would you like to come up with what, and how much fidelity you would like to have? Right? There are those which go to the extreme left, which is that they provide more and more details, and it takes more time. There are those which go to the extreme right, and therefore they can more quickly produce results, but with less adaptive detail at the beginning at least. You can always, one of the interesting things about ΔQSD is because of the rewrite rules, you can always drill down upon request. So and ΔQSD has mostly focused on those two. This picture is not the most up-to-date that we have in our minds, but it's the most up-to-date that we have. There are other dimensions to this. Please.
It's a good example. I've worked with people on discrete systems. I actually worked with people producing chips. When we did that, we ended up time packets. So they then built an FPGAs, right, which was then a scale version of chips. Right? So there's a sort of fidelity range, like temporal fidelity range. But when you get to building an FPGA version of a chip before you do it, that's a hell of a huge amount of investment. Whereas the right hand gets to be, a few algebraic manipulations, and you've got a few years of that. it's worth pursuing example. That's all. I mean, that's all we're saying here. We're not giving guarantees that it will work, but we're creating to come to the great guide. We need to find areas of depth. Right?
Well, it's the essence of the model.
Yes. Yeah.
Right, that's very wise of you to say, but it's often often you know, construed the other way around. So people think that when their model works, it implies that the reality will also work. Whereas our ΔQSD is keen on stating that, you know, it's about when the model doesn't work, it implies that the reality doesn't work either. But it's not the other way around. You know, that's important.
The best moments mine we did some benchmarking experiments in a radio array, and the student came to us, you know, model results disagree with the benchmark.
Right.
There must be something wrong with the benchmark.
Reality is wrong.
Right.
Reality.
Yeah.
Actually, we had a situation where I had that to me, and they said, and the reality is wrong. Your model's wrong. I said, we have 15 buffers. I said, no, you don't have 6. Right? We later come back and said, so basically, the maths was what I was saying is the model was right. The reality, their model of reality was wrong. I totally get it.
Right. And the idea is that, you know, you put more into the detail of the reality you would like to capture. These kinds of mistakes are more likely to happen. You know? So I'm going to show you a bit more of the squigglies. Now, mind you, though, that well, the details of what I'm going to show you are not on the slides. They can be shown. They can be looked up in these 2 papers at last. But it's also important that we notice that ΔQSD isn't just about timeliness. The only resource that we have in there is not just time. There are other resources that we have some theory for. In particular, we have some focus on ephemeral resources. But I'm not going to show that here. So some of the algebraic results, for those who have a love for algebra, we have worked out which of the 4 operators that we have constitutes which algebraic structure. So, for example, the alt finish forms. I'm going to read it because I will otherwise. Yes. So it's a commutative monoid, and at top and bottom are it's the identity and the absorbing elements. And so, if you're an algebraist, you would like to know what the combination of those things are. And the thing is that because the first to finish and last to finish don't combine in the distributed ways, then therefore you don't get to have the richer algebraic structures. Now, there is a set of equivalencies that we have proved in our paper. Here is a selection of them. And in the cache example, we saw this one, which says that an outcome followed by total failure is like total failure itself. So if, for example, this guy fails, this guy, so if the network fails, your response will never come back. Right? So the way to read that is that it's just as timely as a total failure itself. Now, these 2 also we used when we were doing the accumulating the failure rate out. Now we have a bit of distributivity, you can distribute the 3 operators why don't I just use my impressive technology? This is the name again. I remind, impressive is the name of the renderer that I'm using. So yes, so these operators, so long as you are observing time, and that's this funny thing that we have here, right? So long as you're observing time, these three operators distribute over probabilistic choice. That's what this theorem is saying, and that's distribution from both left and right. Now, a bit of more of the theory that we have developed. Now, these particular four equivalences are important for reasons like the one that I showed you, for working out very quickly the failure rate of a system, because they help us. For example, this one, the one at the very top, help us with working with pushing these bottom signs to the top level, right? And as soon as you get it to the very top level, you can say that, okay, this particular design has this particular failure rate, right? And so just to,
Can I just say,
please.
Because you can symbolically represent those failure rates, you do something great. So you can basically work out the, this allows you not to hide. One of the things you want is not hidden effects. In any design, you want to know your risks, right? There's obviously risk.
Yeah, yeah, and yeah, you have that example about the bubble on the wall. You want to
What was in the wallpaper?
Yeah,
right? You want to push it on something so you can notice.
Right, you want to
push it behind the picture frame.
Yeah,
and then find another.
Right. So now I'm going to show you a bit of the proof of this. Actually, the proof scheme, which is the longest one of the four, and this is the one that was a bit unexpected to us. So we were working for some time on trying to do something that looks like rather like the one above, and we realized that wasn't possible until we worked out this. So what is to notice here is that the two operators to the left are both probabilistic choices, but what you get here is suddenly a first to finish to the right. See, that's what's a bit surprising. Now, how do we prove that? Well, basically, when there is an equivalence, we use the big set of squigglies that I showed to you for the compositional computation of the delta Qs in order to show that the delta Qs of the two sides are the same. However, there are this being an algebra, this being an algebraic development, we have worked out a range of lemmata, and there is a proof technique that I personally am particularly fond of, which is the properization theorem. I'm not going to show that, but I'm advertising it here, which we use for refuting results. But let's get to prove the guy at the bottom. Now, so the way to do that is that you start from the left side, the left-hand side of this equivalence. There are two bottom signs here, right? And you would like to kind of push them to the top, right? Work out some sort of redistributing of the parentheses. So, and what you're seeing here is that I'm distributing this. I'm distributing this one. Sorry, this one over this one, right? And so it's left distribution, and then I get this one. Then I realize that this can be shrunk to this one, and then I distribute this and that, right? And again, I perform the same kind of shrinking, and then I perform some variable substitution, and I get this one. notice that at the very top, and I need to go back to here. So you see that there's P1 and P2 here, right? We want to work out the percentages or the labels here for P, Q, and R, right? Now, when I do the variable renaming, the variable substitution, the thing to notice is that, well, unlike here where the variables are only P1 and P2, what you get here is this new guy, P primed and Q primed. You do a bit more of variable substitution, you get to this guy, P double primed and Q double primed. And then once you have made it thus far, right, you see that the bottom sign is at the very top, right? And then you can work out, because this is of the same form as this, where the bottom sign is only at the very top, right? You can then equate the labels, and you get to solve P double primed, Q double primed, and R double primed for P and Q and R, and you get to the result, right? Now you notice that here we used a lot of lemmata, and we used variable renaming, variable substitutions later on. So with those, we have a cheat sheet. This is in our JLab submission. There are 2 cheat sheets shown here. I'm not going to delve into the details, but it's important that if hopefully in the future we get engineers who would like to use this is their help.
This also helps formation tools.
Absolutely.
Basically, we have a people want to work solid tools, but it's new representation, and also
standard. Right. So, like Peter, what is this thing that the Kirchhoff laws and all that?
So
like,
electronics.
Yeah.
They have lots of these things: Kirchhoff's theorem, Dependencies theorem,
Yeah.
theorems.
Yeah. So this is
there's a lot of algebra in
correct.
computing circuits. So this is similar thing for outcome diagrams.
Correct. Yeah. So someone used
the way I see it.
someone proved those things some time ago, and then nowadays engineers just use. Be reminded, please, that this is only about timeliness. This cheat sheet is only for when you are concerned about time.
They're only equivalent to
Time, yes.
Not
Correct. Yep. So in summary, there is an ongoing project on the formalization of ΔQSD. I would like to again credit PNSOL for the ΔQSD itself. This part of the lectures is only about the formalization of that. We have an ongoing project. We, like Neil just pointed out, we use these algebraic manipulations for tool support, and some of that is explained in our JLab submission recently. There is properization where the ordinary techniques that I've just shown to you doesn't work. You can use that magic wand and it works. Now, one thing which was a bit unexpected is that improper rounded variables don't have a lot of theory attached to them. And so, interestingly enough, this is the first body of mathematics for improper rounded variables.
They are mentioned in 1966 in the book. For half a page, when they say there's no
Right. Okay.
Yes.
Oh, I should show those. Okay. Any questions?
I mean, there are a lot of other algebras out there, right?
Correct.
So what do you think distinguishes this from theirs? And where is this exactly in terms of tools?
Well, the second one is easier to answer.
Yeah.
We are at the infancy of our tool support. Not to undermine it.
We're not But basically, the tool support gives you the ability to represent expressions and solve things. We have someone else working on this. We had to get around the problem of the integration and differentiation of the derivative felt function working, because otherwise it produces rubbish.
Right.
In the part we have a previous tool which in a partial symbolic or partial numeric representation can implement we like those numbers and that, but did other things. But yeah, that's where we're at. So as you say, in terms of algebra, right? We don't have the algebra is just basic. Simplify things. I mean, I don't know what if you look at what process algebras have been used for, they tend not to use very large systems.
Because they can't scale.
And scale, and this, I don't know when. The thing about this is because you can actually compact an expression you can always decide to approximate a subtree of an expression to get some level of scale, right? If complexity. So I'm working on stuff where one of those delta keys is the time to complete a transfer on a TCP, given their conditions, turn into a function, which you describe that, i.e., you can ignore some of the detail and abstract that, and then go into it later if you want.
You can ignore as much of the details as you'd like. That's how.
Yeah.
One of the important factors. The other important factor, I think, is the fact that we can do probabilistic choice. Right? Probabilistic choice allows us to hide a lot of the how question. We don't really care about the how. We really care about what. Right? What happens? What we gain. Right? This is important. Now, I think another important piece of answer to your question is that we didn't develop an algebra because we wanted to be pleased with our algebraic properties. This is a practice that was being exercised for decades by PSO, and finally IOG, hooked me in to do the mathematics that can explain it. Right? Now, if there is an algebra, it's because there was once upon a time a load of real world, what is called large-scale experimentation. I don't know how much of that the other algebras in your mind when you ask that question are.
Well, one of the other was correctness. Looking to prove properties.
Right. Whereas we rather about disproving wrong properties.
This one is timeliness.
In particular, yes.
So this, I don't know really if many algebras or any that is.
There are some algebras for things like min-max. There are min-max algebras related to things, right? But they give such use values they're very difficult to work with. There are discrete time algebras. There's topics work like this, right? The stuff that we more to do with Iterative final systems to Right. So if you say in that's the field I know about, right? I'm very different.
Okay. Thank you very much, everyone. Yep. Thank you.
So welcome to the final lesson. Final lesson, I want to talk about two main things. So first, I want to use the whole ΔQSD to design a real algorithm. This is the Cardano Shelley block diffusion. And then I want to show a very important thing which happens very often in real systems, which is overload, temporary overload and permanent overload, which are two very fundamental things. And so we have lots of interesting things to say there. So first about Cardano Shelley. Okay, so some context. In the case studies I presented before, we used ΔQSD for diagnosis. We take some existing system which is not doing the right thing and we try to find the problem and fix it. Okay, but so that works, but that's not really the intended purpose of ΔQSD. The real intended purpose is to design systems using it from the beginning. Prevention, not cure. So I'm going to show you an example of that. And this is the Cardano Shelley algorithm. So this is part of the Cardano blockchain supporting ADA cryptocurrency. So this is not going to be a big blockchain. It's only a small part, okay? So a part of Cardano is called block diffusion. So this allows an authorized node. So you have a set of nodes to create a block and to add it to the most recently created block. So the context is that there was an initial implementation called Jormungandr, some Nordic influenced name, but it didn't really perform well. And the second implementation called Shelley, which is what I'm going to talk about, used ΔQSD to guide the design.
And we should say, even what we said earlier, it's written in Haskell.
And it's written in Haskell. And the original one was written, what, in Rust? Jormungandr? So there was this thing, it's a no-brainer that Rust is faster than Haskell. Wrong, okay? So that is a total red herring, the language that it's written in. So Haskell is a much higher level, and Haskell is seems a better level of abstraction for this kind of
It
problem.
has a much better fit for codes problems than almost any other language.
Okay, so I'm going to present part of this Shelley implementation, so the current one written in Haskell and which was done using ΔQSD. Okay, so it's part of the part of the blockchain that I'm going to talk about is called block diffusion. Okay, so a little context on blockchain management. So I'm going to show a part of the design problem of the Cardano blockchain. So this uses proof of stake. So a blockchain and distributed ledger. So a ledger is a book in which you record financial transactions. Okay, it used to be done on paper, but blockchain is a distributed, secure version of that, and it uses a chain of data blocks that are witnesses, cryptographic witnesses to the correctness of preceding blocks. So it basically guarantees the correctness of the ledger. And in order to agree on the sequence, use a distributed consensus algorithm. And in Cardano, this is called Ouroboros-Prous consensus. So it randomly selects a node to produce a new block during a specific time interval weighted by distribution of stake. So this is the context. So the Shelley block diffusion algorithm. So you randomly choose a block. And so in order to do that, you need a copy of the most recent block. And so the most recent block has to be copied to all potential block producing nodes. So this is a kind of broadcast diffusion. This is called block diffusion. And that's what we're going to design. We're going to design the block diffusion algorithm using ΔQSD and to make sure that it's satisfying some very important timeliness constraints.
What is the time constraint? It's like what? Bitcoin's once every 10 minutes and Ethereum's once every 50 seconds. Because
Exponentially distributed 20 seconds in.
30 seconds.
20 seconds. The block has to be distributed to 95% of the state within 5 seconds.
95% of the stake, which is basically 5 seconds.
It currently achieves that.
In 5 seconds globally.
No, it doesn't achieve that. It achieves it in 830 seconds. 800 to 1,200 seconds.
No. Yes, astonishing.
Thank you.
Astonishing.
Right. I know that some people like that. That's the way to do it.
What? The other thing to say about this,
Yeah.
right, so there's stringent timeliness constraints, there's also stringent resource constraints.
Yeah.
In that we do not have a global broadcast network to do this over. Right, so there are you could easily think of an algorithm that would do this where maybe we just have something on future geostationary satellites and stuff, right? That's not what's happening.
Okay, I'm intrigued.
Ah.
This is usually, so, and this is being done over the
with all its adversarial
right?
qualities.
No private wires or special private
The
networks.
public internet.
It's the public internet.
Okay.
Nodes are distributed globally anywhere one wants.
Okay, so now that people are interested, so the problem statement. So we have a node graph. So nodes know some of their neighbor nodes. Okay, here we can see a kind of image of this graph. We take two randomly chosen nodes, A and Z, and we determine the delta Q between them. So this delta Q has to satisfy certain constraints. And what we do know is the delta Q XY between pairs of nodes, okay, and that are neighbors. So we have some design parameters. So this frequency of block production. So we know this graph, we know the block size, the forwarding protocol, block processing time. So these are parameters, okay. So we need to design this algorithm. And we're going to use ΔQSD. So this kind of is a template for how ΔQSD is used to design algorithms. So we do it in two steps. So in the first step, we have to know the basic delta Qs, so the delays between the randomly chosen nodes. So that's a preparation step, but that requires some serious measurement and computation, which I will show you. And then in the second step, you have to design the actual algorithm about how the diffusion is done. And so this algorithm then is designed, for example, which neighbors do I contact? What are the conditions under which the blocks are forwarded? Do I divide a block into a header and a body and ask authorization, smaller, bigger? There are number of different possibilities. And so you want to compute the delta Q for these different possibilities so you can actually find what is the best algorithm. So if you look at the diagram here, so this is kind of a collapsed version of the design space tree you saw before. So the initial design, you have one hop, okay? But maybe you want to do multiple hops to get to a node or split the header and the body. So because the header is much smaller than the body, so you have to decide where to go to. Maybe you don't want to always send the body. What if a node leaves and rejoins the network? So that also, it may rejoin in a different place. Also, you need to select which neighbor you talk to. Some neighbors are faster than others. So here, each time you design on something, there's a decision here. And if something is not acceptable, you return to previous, you make another decision. So you're kind of moving back and forth along this chain and looking at different outcome diagrams and computing delta Qs all along the way, okay? Okay, so that's how it works. So the first step is you have to know the raw material, delta Qs, before you get to this part. So this is going to be a very performance measuring part of the talk. So you want to measure the delta Q between two internet nodes. So there's some preliminary work here. So first of all, what are the factors? So the block size goes from 64 kilobytes to 2 megabytes, or in 5 steps. The network speed, well, that's the measured TCP speeds. Geographical distance, we're assuming 3 distances. Short, which is in the same data center. Medium, which is on the same continent. And long, which is on different continents. Okay, so it's kind of not so fine, but that's fine. And then the next congestion, we ignore it. So we will do first single hop delta Q, and then multiple hop delta Q. Notice the multiple hop delta Q is computed from single hop. They are sequential compositions. So we're going to do convolutions there, okay? And then once you have these multiple hop delta Qs, you can have many paths going between source and destination. But what you need is a random path. So you will do probabilistic choice, a weighted sum to find the random path.
Stop the horrible architecture. I just tried to do some straight. I was getting ridiculous p heights because it wasn't going to straight. It was going to edge cloud.
Okay, so it turns out that this governs again, but this system is it's actually it establishes connections to peers TCP connections, and just that bearer as an underlying bearer. It then multiplexes multiple connections, not TCP. That problem resolved too, right? Right. And so basically the notion is each one talks to 20 different something talk to 500. They accept connections. They diffuse the data. And it turns out that the system builds a spanning tree. The headers are left for one packet. So the packet builds a spanning tree from the source to the endpoints. So basically, the reason why it's so fast is that single packet is finding the shortest path. Right. And the numbers I'm looking at here is we're effectively diffusing the last three blocks, 0.44 of a second, 0.29 of a second, and 0.33 of a second.
Yeah, so the algorithm, when it actually runs, it looks at different neighbors and it picks
Well,
the
it's
quickest one
in some
in
ways,
real time.
it actually is the other way around. It's sort of the header propagates, and then the receiver says, who am I going to get it from? And it has knowledge of recent code. So it uses recent history to make a decision of who would be the best to talk to. And it makes that as a conditional decision. But if they don't use it at the time they're supposed to, because we have a history for that, we go find something else. Right. So so it's basically use the best knowledge, but trust anybody in this process. Right?
Okay.
They can also understand.
So the general philosophy is use the information you have and trust it.
And the whole system is built with no global information. Everyone needs their own global information.
I mean, it's quite astonishing. I mean, basically said I'm going to make it as low as I can to make sure that it's a stable propagation around. He reckons that's somewhere around 7.
We are honestly worst case. Or we propagate each other. There are other reasons. There's a whole. They're basically.
And this is the actual block propagated, not just the header.
This is reaching. This is the header and the block reaching 95%. So. And there's also 4 worst conditions.
Okay. I mean, this 95% stable condition is kind of curious to me. That could also affect your
No. That's an outcome that's very interesting.
Okay.
But
you don't actually use that in your routing. You don't necessarily go direct this at the state. You know, because you just blast it around as well.
You can't know that. Right. You can't know that with certainty because that implies transitive information.
You would have to trust things that people told you.
Yes.
Yes. On what we were allowed to make the design decision with all those arguments on the table. Right, we said, no, we can't trust anyone. We've got to do this, but we argued through together.
So I'm only going to talk about a part of all that, some pieces of it. So the measuring of the delta Qs. So we measure the first on the top here. We have the 1 hop per block size here. So you can see the different block sizes in the different colors. They're from 64K to 2000K. And then you do a multi-hop here.
So basically, TCP connections seeing windows. So basically, what you're seeing there is the round trip times window open cost. We assume the window is closed, but we use connect. So we're not paying the first round couple of hundred pounds to set the connection up, but we are paying all costs. And that was making it, having the connections established. We did that to basically mean that we could make certain things to you can achieve these kinds of because we don't understand.
Right. Yes. Right. So you have like
we have an overlay network that's managing itself all the time. Yes. Cool. Right. Anyway, sorry.
Okay, no, it's okay. You're completing things, so it's fine. So here I'm only showing the ΔQSD directly related stuff. So once you have the single hop, you can look at multi-hop and see. So So this fact that the single hop is not that detailed is not really a problem, because once you start going into multi-hop, then you get a lot more detail added, in fact. So for 64 kilobyte on the left and for 1000 kilobyte on the right. So from 1, 2, 3, 4, 5 hops.
Okay, so this is where this informs your design decision.
Yeah.
Okay,
Right.
so you can look at this and say, okay, this is our target diffusion time.
Right.
Okay, and therefore, how many hops can we afford?
Yeah.
And then that tells you what something you have to do in terms of your overlay graph construction.
Yes.
Right? So that's the way around this argument goes.
Yeah.
So you take this information, and then you use small world graph theory to say
How many thousands of nodes on 10,000?
right. So you take the small world theory and say, okay, if I construct a random graph with the valency of this, what's the number of hops I expect? If you can compare those, and therefore I can work backwards from this to the valency I need in order for the random graph I construct to have few enough hops that when you do this, it will arrive in time.
Right.
That's the way that particular.
Okay.
Wow.
Okay, so this is a more detailed where you actually look at different paths.
Yes.
Paths have a given length in the random graph. So this is depending on the block size, okay? So the transfer delay. So you can see here, you can go from very, very fast for the small ones to slower here. So this is paths of given length in a random graph. So I'm not sure exactly how you weighted them, but
Well, so actually what we did is we worked with some people at the National University. One of the yes, right? But it wasn't the university, I think it was and we basically looked at which short, one and a half lengths and what was optimum, how making decisions on local decisions, how and came up with some.
You also have to like want to make sure the graph is a partition.
Yes.
So it's not enough.
That's
It's
a big
not.
problem, yeah.
It's not good enough. It's not good enough just to choose your nearby neighbors.
No.
That will give you a fast result, but it's a high probability of the thing falling complete.
Yes.
Partitions.
Right.
So you need to choose a mixture of nearby neighbors and far away neighbors. Simulations work also.
so this is the small world notion, huh?
What's the frequency with which you
Yeah.
make those long?
You have to go, some of them have to go far away.
There's more in it.
Yeah.
All of that went into the design.
So there's a lot of subtleties, whereas I'm only giving a piece of the iceberg. Huh? Okay.
This stuff, right? There wasn't any theory for, right? How do you do the performance analysis? We have to build the performance side from scratch, right? And we had so many arguments with people about how to do it. And eventually, servers all over the world measured them and said, "Go and tell me why I'm wrong."
Yes.
Okay.
Anyway, sorry.
Okay, so now we have the delta Qs, our raw material. The second step is the actual algorithm itself. So here, when we have an algorithm or a proposed algorithm, we have its outcome diagram, and we can use that to compute its performance, its timeliness, okay? So here we have an outcome diagram, which is a part of the system. So this one, basically the idea is you obtain 3 blocks from the fastest neighbor, you divide blocks into header and body, and you ask permission before each time you do a transmission, okay?
So you propagate the header first, and then nodes request body. You get
Yeah.
Request the body, and basically they can request the body from anything. Right, because it keeps the body that they request. And then what you're doing is effectively looking for choose the right speed for the first synchronization.
Okay, so I'm thinking this will be resource constraints. So you don't go and ask for the block from everybody before you have it, because now you're putting too much load. So the trade-offs you have to take from.
You do it from one node because they can let you down. You do it from 10, that's a large resource. Is the answer 2 or 3?
Yeah.
And this is the decision.
So that's, you have to explore that space And so here, the outcome diagram lets you compute what the timeliness is for a particular design decision. So one of the steps, so this, the all to finish and first to finish. I don't explain it again. So here we can go more into how it's working. So if you look at the top left here, okay, so you ask for, so Z and A are the source and destination, if you can read it. So you ask for the request for permission, then you obtain the header before the body, and then you have these 3 all to finish ones, okay? And within these, you have a first to finish. So here you will ask 1 block body from the fastest neighbor, but you do it for 3 blocks in order, okay? And you're dividing it into header and body. So this is the result of one particular design decision. But once you have this, and you have the basic delta Qs, you can say, without actually running, you can perform, you can already compute what the performance of this thing is going to be, fairly precisely. Okay.
I mean, so this, my mind's racing ahead. I mean, this is like,
Well, syncing blockchain in the first place is actually that's another problem.
yes.
Where the performance
And
is
we have noticed in trying to sync it here in months.
Okay, right.
It turns out that in Cardano and in the data, the CPU is basically going through the steps of validating it.
Yeah.
It's the CPU that's involved.
Right,
Yes.
so getting it is not the problem.
Validate.
Checking that it's correct is
Yeah,
right.
yeah.
So basically, it comes down to how fast the CPU is. Right? So,
It's actually not an IO bound problem.
So this was done by hand by the P and Sol guys. So this is timeliness, huh?
So the syncing is a throughput problem,
Yes.
whereas this is a timeliness problem.
Yes.
They're different.
Okay. So once you know these causal connections and these synchronization operators, you can compute the timeliness, okay?
We should point that code for the recording. It turns out this was an intermediate design. You know, better than this, but in order to get it right, but particularly this was something that was suggested. We could critique it. Right? They ended up doing something faster.
Okay. So that's it. That's all I'm going to say, because this shows basically how ΔQSD helps the design process in computing the timeliness. So there's a paper that says more, but the answers from the developers here present here, I think they have said more publicly than has been said before on this algorithm, no?
It's not that much of a secret, right?
Isn't?
No, it's open source.
Because it's open source, but not much has been published on this, right? I think.
It's difficult to find an audience that wants to listen.
We have a model conference in July.
What is the name of the conference?
It's called Marble, which is mathematical research for blockchain economy. It's all about applying mathematical models to blockchains.
And to what extent of the data would you be interested in?
Well, I think a lot of people would be very interested in how this kind of time
Would it, for example, be of interest if we just tailor?
Well, let's
Yeah.
talk about that.
Offline.
Actually, the answer might be, we might not be the right people. Network engineers, it depends whether it's an engineering conference or research conference. Right, okay, so let's talk about it, because the subset is probably on us. So is that not
just this section probably tailored to not have to have all the production to the Delta.
And it turns out the real world measurements, for various reasons, we designed to worst case, right? What we're seeing there is the credible worst case. In real life, the average are much faster, but we also have a whole series of models into the workings on the critical part. Might be very interesting. People says, actually, this is how we model
Wow.
timeliness.
I mean, who doesn't want a timely high performance blockchain? Yeah.
Thanks.
Central government. It turns out there are restrictions. can work out, there is a restriction. It turns out that the global central banks can do shortcuts of trust, which mean that the global distributed, decentralized, whatever blockchain can never perform it. Right? Banks have got a dominant position because they can do trust and they can do this. Right? Anyway,
I haven't printed so much money than you. Let's carry on.
Okay, that's all I'm going to talk about blockchain. But now I'm going to talk about overload, which is another very interesting problem. Okay, so system is designed for maximum load. So what do? Well, one no-brainer solution is over-dimensioning, but this does not solve it, okay? In fact, it kind of makes the problem worse because users will assume they won't know where the edge is, and they will assume that the edge is very far away, and maybe it's not, okay? So the whole point is your system should be predictable when overload happens. And there's actually two very different cases. The first one is temporary overload. So occasionally the load becomes larger than the load that it was designed for. And so the system has to be reasonable. So that's one thing we're going to talk about. But the second problem is just as important, which is called permanent overload. So if the overload happens too often, and there's actually no really formal definition, but if it's too recurrent, something has to be done about it. And so something has to be handled on another level. So you need something called the multi-level system to handle that. So I'm going to talk about both of these. But first, I want to introduce some of the ideas. And one of the ideas is hazards. Okay. So a hazard. So there was already some mention of hazards and slack and slazard. So let me make some of that a little bit more precise. So a hazard is a potential breach of the specification. So in a very broad sense. So for example, here we have a delivered delta Q, and here we have the required one in blue. It's diagram as you see before, but here we have this, they intersect now. So there's some probability that the required delta Q is not respected, okay? So that's called an armed hazard. So if the hazard has a non-zero probability of happening, it's armed. So then we have to be, things are starting to get dangerous. And there's also the notion of a latent hazard. So this diagram here it's intersecting, but in the previous versions, you saw it where it didn't intersect. Well, the delta Q is not just some constant function, it's fluctuating. And if the load gets higher, it moves to the right. And at some point it intersects. And at that point, you've armed the hazard, okay? And the more you overload, the more dangerous the armed hazard gets, okay?
Now, the risk is impact times hazard. So you can't just say, you have to look at the impact of hazard being armed, but at least you know knowing that you're in that situation. And that's where it becomes system.
Right. So a hazard is a very broad thing. If the system specification is breached, it might be a very minor thing like, a light burns out, but it could be a major thing like Fukushima disaster. So yeah, so there's also the impact and the risk, which is the product. But it's an armed hazard is a dangerous thing. Yeah.
Hold that metaphor, because an armed hazard doesn't necessarily mean the system will fail.
Yeah.
It only means there's a chance that it might fail. So if nobody goes down the dark alley where there is an armed hazard, nothing bad happens. That's what we might. Right? Yes. So just make it clear what we mean here by a hazard. Hazard is not the same thing as a failure. No. But a hazard is now a probability.
Potential.
It has this probabilistic nature.
Yes.
Okay, so this is the general thing, and it's actually very broad, but I want to narrow it and focus just on overload and timeliness hazard, okay? So the delivered delta Q is a function of the offered load A. If you overload the system will get slower, and that's what we're going to talk about. So if you have a high load, the delta Q will get worse, and that is a typical way to arm hazards, okay, is to increase the load. So you have to, when you design for overload, you have to do that within your head the idea that you are able to arm hazards, okay? And there's actually an order that has been defined for these hazards. So I'm not going to go too much into these orders, except, so the first three are more things that happen during normal system operation. But then once you get to behavior, internal correlations, so this is when the system starts shooting itself in the foot in some way, and one part of the system starts interfering with another part, or one part of the system fails, causing another part of the system to fail, etc. So that's called an internal correlation. And the final one is external. So this is, for example, when there's a natural catastrophe which causes the telephony system to be overloaded because everybody wants to make a phone call. Okay, so these, yeah. So that you design for that. Huh? So the idea is to design for these internal and external correlations. Okay, so that is all setting the stage. Now I want to give a simple system model. So during the previous lessons, I talked a bit about MM1KQ. So now I want to give a simple system model. It's going to be very simple because in general, it could be very complicated. A model that we can analyze, and simple enough to analyze, but complex enough that actually it gives intuition on reality, because I want to give intuition here. So here, the system will be a component from queuing theory. Okay, so the input, there's many independent tasks coming in, and the component is treating them like as in queuing theory. Okay, notice this is only one component. In ΔQSD, you could have, of course, a more general outcome diagram for systems that would be more smarter and more precise, et cetera. But I'm not going to present that here. I want to use a real simple model, but that still gives you the right intuition, okay, for our presentation of temporary overload. So here is the model. We have a system. We assume it's a component from queuing theory. So what does that mean? That there are queuing theory components have several parameters. Okay, there's a buffer inside here, and there's a server that performs some kind of task that does the task. So it can store a certain number of tasks in the queue, and they're performed in, first out. So there's basically 4 parameters. There's 2 inputs and 2 outputs. So the input is the offered load, which is typically written with a little a. This is the arrival rate of messages, tasks per time unit. And the buffer size k is how many pending tasks can be stored inside the system. And then there's 2 outputs, which is the delay between an input and when it finally gets to the output, and a failure rate, because sometimes messages could be dropped, maybe when the buffer is full. Notice the D and F are kind of corresponding to delta Q already. You can see the relationship here. Huh? Okay, so to be more precise, so here is what's called an MM1K queue. So there's, in queuing theory, many different kinds of queues, depending on how the queues, how the servers, how things are handled. So MM1K means that the arriving messages are exponentially distributed with a rate lambda. So basically it means they're independent. The messages, they're not really correlated with each other. And the service time, the second M, means the service time also is exponentially distributed with the rate mu. The 1 means that there's only one server. It's a single core machine here. One server can its time. And K means total buffer size is K. So which means you have K minus 1 here and 1 in the server. So K in all. So the offered load A is basically lambda over mu. So mu, 1 over mu. So though if it's equal to 1, if A is equal to 1, that is the normalized amount of number of tasks you can actually handle. Okay, but it doesn't mean you can actually handle that many because they're exponentially distributed and they might get bunched up, and we'll see what that does. So the 2 knobs we control here are offered load and buffer size. So notice one of these is like dynamic and changes when the system is running, offered load. Buffer size is more like a fixed hardware limit. Huh? Okay. And what happens is when the offer load increases, both delay and failure increases. So when the buffer is full, so assume this is completely full and new messages arrive, in the MM1K, any new arrival is dropped. So that is the source of failure in this kind of queue. Okay, so this tells us the basic queue. And now let's see what we will tell the story of temporary overload. Okay, so yes, we want to build a big system, bigger than what anyone has built before. And we're real experienced. Okay, they exist, we do exist. And we use our experience. That's called inductive reasoning. But inductive reasoning is kind of a flawed way. We have to be very careful, because if we do things that have not been done before, new phenomena appear, okay? And there's some kind of a cliff, and the system will work well until we reach this cliff and jump off the edge, okay? So the question is, how can we design the system, even though it's not perfectly performing, at least to be predictable and reasonable when we fall off that cliff, okay? Because we will fall off the cliff, okay? So we will fall off the cliff. So some stories on that. So what's the no-brainer solution? Just increase capacity, right? So there's some, so I summarize here some stories. Some big companies, and I will not name the main one that I'm thinking of here, solve it by multiplying capacity by 2. And in fact, if you have multiple levels of management, each one multiplies by 2, so you have a 2 to the k over dimensional. This is not a joke, okay? This is not a joke.
Not just laughing at the system doesn't solve the problem, but pushes it to go into.
No, it pushes it. That's exactly what happens. It does not solve the problem. It pushes its occurrence beyond where one I can identify which of those managers is responsible, okay? So that is really what's done. This is not a joke, huh? So, okay. Okay, so the surprise, it does not solve the problem. So what happens when you increase the capacity? Users, initially, they're happy and they become more demanding. They start doing HD videos or 4K videos. People who never did videos in their life start doing videos and more and more. So it's like drug addiction. You will always have overload, okay? You will not solve it by overdimensioning. So it actually makes the problem worse, because when the overload does occur, it occurs at a bigger scale, okay? So that's not the solution. So what is the solution? The solution is you need some design principles to make the system predictable when the overload happens, and it will happen, huh? So here's a simple slide summarizing the basic 3 principles, which were found by long nights of sweat, blood, and tears by the P&Sol guys. So the first design rules. So these are key design rules that your system must satisfy. First one, when your system is overloaded, it may behave badly, okay? Clearly, it cannot do all the work, but it should not break, okay? When the overload goes away, the system should go back to normal, okay? So the idea is that it should be ballistic. Ballistic means that it's an open loop, kind of like ballistic missile, huh? When you launch the missile, the behavior is predictable. And if you launch many missiles, even if it's bad. And the emblem here is actually the motto of the city of Paris, which is fluctuat nec mergetur, which means it is tossed but does not sink, which means a boat in a storm will be tossed around as long as it does not sink. When the storm goes away, when it calms down, the boat can resume its trip. So this actually summarizes this. This is the actual motto of the city of Paris. This summarizes this first rule. Okay. The second rule is when this is overloaded, there must be some guaranteed minimum functionality. It must not go to 0. There must be, for example, some high priority packets that still pass. In the military jargon, the emergency action messages, as the P&Sol people know, should still pass, even though the others don't pass.
And if you were designing a system to run small cells, for example, if you had a situation in which the control messages would still pass, the cell would not collapse.
Yeah, so the small cell control messages were not allowed to pass, even though so they should be allowed to pass. And finally, when it's overloaded, the system is still accessible to management. There must be a separate management interface. You should be able to observe the system and maybe take some action or whatever, or at least see that what's going on when the system is overloaded, okay? So those are the three rules. And now I want to show you a little bit what happens when you have temporary overload, the effects, okay? So the first effect is, so let's take a look at the value of the load. So if you have low load, okay, which something like 0.8 or less than 0.8, the normalized load. So this is fine, okay? System behaves very nicely. And if the load is very low, it's even superposition, which means that the amount of work is just the sum of the work for each packet. So it's very nicely linear. But when the load gets high, some messages will be dropped. So there will be failure when A is equal to around 1, but it actually starts getting bad already around 0.8. The problem is the input packets are exponentially distributed, which means that some of them will bunch together. So once you start getting close to 1, there will be periods when it seems like you're actually at or even greater than 1 because of that. So when you start approaching 1, things get very bad. And when the load is much higher than 1, the failure rate will tend to 100%, okay? But in a very predictable way, which I will show you, the delay increases to K, which is the buffer size. So the switchover occurs somewhere between 0.5 and 1 load. And one lesson is temporary overload gives a long-lasting increase in delay, because what happens is the buffer fills, the K elements get full, but you can only empty the buffer at the speed at which the elements are serviced, okay? So this diagram again comes from the small cells. So the buffer fills quickly and empties slowly. So temporary overload causes buffers to fill quickly. So basically there will be long-lasting, that's the first lesson, there will be long-lasting hits in performance. But that's not all, okay? We can say more. So first of all, how can we tweak this? Can we help by, we have these two knobs, okay? So of course, the offer load A. So yeah, as I said, when it's approaching 1, you have bunches of tasks. So once you get close to 1, it's over, your system is overloaded. The only way is to decrease A, okay? So during normal operation, it should be well below 1. And the second thing is the buffer size, okay? So bigger is not necessarily better, okay? So buffer size affects the trade-off of failure and delay. If you have small buffers, it will increase the failure rate because the buffer will fill better, but it will reduce the delay problems. So if you do things like interactive video or gaming, it's actually better to have small buffers, whereas large buffers will reduce the failure rate, even though at the price of having sometimes long delays. But if you're doing like file download, then that's usually maybe not a problem. Okay, so now I want to show you kind of from this model what happens exactly when you jump off the cliff, okay? Basically, what happens when the load starts to go to 1 and it starts increasing? What happens right there? So this is very interesting, actually, huh?
This is all that in the GCP.
Oh yeah, so,
Destroys
okay, but there's some very interesting lessons here because it's very predictable, actually. So this is all from the MM1KQ, but in fact, there are these are more general lessons that it's in some sense a general complex system issue. Huh? So the first thing is the maximum fluctuations happen at the edge. So when the load is normalized to 1, the delay for every single packet will fluctuate depending on how full or empty the buffer was when the packet arrived, and it will fluctuate highly. And I will show you the delta Q in a minute. So the system, which was very calm at low load, becomes very wild right at the boundary. But then when you start overloading the system, it calms down again, which is curious when you have a very high overload. So what happens is the output then is basically constant. It's just the system does what it can, but the packet loss is very high, which is A minus 1. So if the overload is a factor of 10, so 9 of that 10 will be lost and 1 will make it through, okay? So here I have a nice picture of it. So I have the cliffs at Dover, which shows, it's very nice. So we have three situations: low load, critical load, and high load. So low load, the system is stable. So superposition principle, it's very linear. If you do two tasks, the amount of work is the sum of the work of each task. So how nice can you get? Okay, packet latency is low, predictable. Life is beautiful here. And at critical load, the packet latency is unpredictable. It can fluctuate from 1 to k. However, if the load is actually still strictly less than 1, the loss rate will still be some sense low, 1 over k plus 1. So if you have a big buffer, you will still have fairly low loss, even though it's a huge fluctuation. But at extremely high load now, much overload, factor of 10 or 100, the system again becomes stable. It's basically running at full saturation, okay? The loss rate is a minus 1 over a. So if a is equal to 10, it'll be 90% loss, okay? The packet latency is high and predictable. So I'm assuming the packet loss decision is made upon entry into the queue. So once the packet is in, then it knows it will make it all the way through in a very nice, predictable way. Of course, probably it won't make it in. So the decision of entry, of loss is made at the entry. But once it's in, it's very predictable. And you can actually look at the delta Qs in those three situations. So these, I computed them from the formulas of MM1K in the book by Arnold E. Allen, okay? So at very low load, you can see here, so you have this negative exponential. So as the load decreases, the delay is small, and the lower the load gets, the lower the delay gets. So we have this exponential distribution. I used this especially when I did the iterative query, and the failure rate is very low, tends to 0, okay? Now, at very high load, you have this other exponential on the other side. So the delay is very high. So all the packets that make it through are right here, okay? They have a delay of k, and the failure rate is very high. So everything bunches up at k. And once you are at the edge, you can see it's like a uniform distribution. The delay is the same probability, the buffer has a probability of having the same probability of having any size number of packets inside. So the delay is basically varying from 0 to k, could be any value with the same probability. So you can see how it's stable at low load, stable at high load, and kind of wildly fluctuating in the middle. Yeah?
It literally is a uniform distribution, right? Because that was one of the reasons. Right? They're saying it's running a sense.
So the use of uniform distributions represents critical worst case.
Interesting.
Right? That's one of the reasons.
Very good. Yes.
Right.
Yes. Excellent. Everything fits together. Amazing, huh? And even at the very low delays, you can approximate these exponentials also with uniform. You just ignore the tail. Huh? Yeah. Okay. So yeah. So here that actually. So overload is no longer a thing to be feared. You understand? It's fact. You know what's happening there. Okay. If your system obeys the principles. Okay. So sometimes you see these kind of diagrams, these throughput latency diagrams. So these diagram gives a little bit less information. You can see here at very low load, the green, okay, the latency is kind of constant. So here's when you have the superposition principle. Here in the middle is when things start getting more nonlinear. But at very high load, again, the latency starts becoming more like a constant once everything is full, okay. So this is the diagram you would see if your system is well designed. This is a well-designed system, okay? And an example of an actual system that actually and published and actually obeys this, I'm sure there's others, but this is one I have a diagram of, this is actually a famous example, the Ericsson AXT301 ATM switch, which has its supposed 9/9 reliability, which I'm not sure I believe, but that's what Ericsson says. But if you look at the diagram here, you can see that on the horizontal axis, it's offered load. And at the point where it's maximum, you have 100%, and it goes up to 1,000%. So 10 times, so A equal 10, okay? And you can see here is the call throughput. So up to 100%, it's very linear, it accepts everything. But once you start getting higher, for a while it stays there, but then it starts slipping down. And the problem is because it has to do a lot of work rejecting all that those calls that are being pounded into the system. Okay, so basically, so it actually has, the throughput goes down, but notice the system does not crash. It's very predictable. The throughput goes down because the poor system has to throw away all these attempted calls. Okay, this yellow part. Huh?
Don't forget, this is indicative of being able to do or hack all the version control.
So
But in
even better design systems, this part would be smaller, maybe.
and it is possible, if you know you're trying to design for this, it's possible to design those systems. What I'm saying is, you don't need that much yellow.
Yeah, you have to reject very quickly if you're so you have to know when your system is overloaded and reject very quickly. Here, the rejection is probably happening somewhere inside.
It's happening
the
in the
system.
software's getting
Yeah.
updated to CPU. If you can do it properly, you can basically
A little hardware
no, you
multiplexer.
can align it, in which case it doesn't matter.
Then the system would be, then it would be a perfectly horizontal line here. Okay.
Because actually you can't get to that.
Okay. Okay. So that's temporary overload. So you can see temporary overload is not so bad, right? Now let's talk about permanent overload. And this is another problem. Okay. So assume your system is getting overloaded very often, too long-lasting, repeated, well, too many permanent overloads. They start getting extremely annoying. So this is kind of, your mileage may vary, but assume you have this situation. Okay, how do you solve this? Well, you add resources to the system again, but that's not really a good solution. So the solution is the following. Because a permanent overload is always possible, you need some mechanism that's outside the system, that can observe the system and that can take the required action. And the bottom level is the base system that we saw before. So each new level on top, so maybe you might need more than one, is handling things and will have its own time scale. So then there's a principle called mitigate or propagate, which means whenever you're at a particular level, when there's a problem, you have always the decision, do I handle it here or do I pass it up to the next level? So you have to be very willing to pass it to the higher level. So don't always try to solve the problem at the current level. So Erlang OTP actually kind of supports this, although the levels are not actually truly independent. So this system that I showed before is written mostly in Erlang, but you can see there's this yellow part. That's because there's actually some interference between the different levels, okay? Which is not good. So let me talk about these multi-level systems now. So this is the third part of the ΔQSD. We have our independent parts, we have our couplings, and now we add permanent overload. So we need these multiple levels, okay? Different problems occur at different time scales and need different solutions. So here's our original system. It satisfies its own quantitative timeliness agreement, okay? We've seen what happens under temporary overload, okay? So assume it's well-designed, but the QTA may no longer be satisfied, okay? There may be armed hazards and so on. It no longer provides its contractual service. Okay, so now we build a multi-level system. So we take our original system, it becomes the lowest level, okay? But we need to exchange it a little bit. It must satisfy several new properties. It must, first of all, be extended with observation points. You have to know when the QTA has been breached, and there must be some way of doing things like reconfiguring or restarting. There must be a breach and resume, okay? And then it has to obey the design rules that I presented before, okay? So then we have this kind of a structure of multiple levels. So system one is the base system. If the QTA is breached, then system two will detect that, and it will do what it decides is necessary, okay? And maybe resume system one or whatever. If system two cannot handle it, it goes to system three. So this is the theoretical structure, and I will give you some examples of this. But first, I want to tell a small story, okay, why the levels should be independent. So this is a real life story. So there's a guy called Leonid Rogozov, who is a surgeon, and he was stationed in Antarctica in 60-61, and he had appendicitis during his stay, and he was the only surgeon on the base. So what do you do? Well, he performed his own appendectomy on himself while he was awake, okay, and performed local anesthesia. He used a mirror to observe his inside, and he had assistants who were not medically trained, a driver and a meteorologist to provide the instruments. So it was not easy, general weakness and nausea, but he successfully completed the operation in 2 hours. And in 2 weeks after that, he was back at work. Amazing, huh? This is a real story. So this is not the recommended way to build systems, okay? In this system, the second level is the same as the first level. So the first level tries to fix itself. So this, unfortunately, is sometimes how Java programs are written. There's a problem, part of the program tries to fix. No, that's not the right way, okay? So this is not recommended. Ideally, the independence must be complete. The surgeon who operates on you should not have any health problems while he's doing that, okay? So I thought this was a nice example, yeah?
It is my understanding that to go to Antarctica, the British Antarctic Survey, you have to have appendix.
Or there have to be 2 surgeons, right? You have to have your appendix removed. It's a condition. Okay, so they learned their lesson. Actually, this was an article in the BBC World Service. Yeah. They learned from this. Yeah, so you don't want this situation. Okay, now let me show you some examples. So one example is supermarket. Okay, so this is a kind of classic example. Here we have a supermarket, cash registers, entrance, exit. People queue up, customers enter, queue up, collect their merchants, queue up. And the QTA is, for example, there's less than 5 customers in line. Okay, so not too much waiting. But what happens if there's more customers in line than 5? Okay, well, you have to do something about it. So the second level is you would then have a QTA 1 breach. So the supermarket is on the lowest level again. You have a breach. What do you do? Well, you have possibilities. Well, you open another cash register, you add a cashier if there's one available. You open a self-service. You open the bar and you offer free drinks. You set off the fire alarm, right, Neil? And that will empty the supermarket very quickly. Of course, it reduces the amount of things you sell as well. So the QTA 2 could be something like QTA 1 violations happen less than 50% of the time. But if this is violated, that means none of this actually really solves the problem. You go to an even higher level, 3, where basically the supermarket chain realizes there's a problem with this particular store that has to be solved. So how do they do that? Or they can enlarge the store, open another store, or whatever. But there's a level. So you see there's 3 levels, and each level is at a different time scale, okay? So the customer's waiting, the fixing of the customer's waiting, and then the fixing of when that fix doesn't work, okay? So another example is an Erlang system. So an Erlang program is a system of lightweight threads, send messages, and there's 3 parts for the fault tolerance. So you have primitive failure detection, process linking. When one of these fails, another is notified. Then you have supervisor trees and stable storage. So let me explain in a second just a little bit how it works. So these black ones are the workers. And if one of these fails, so they're linked together and the linking is transitive. If any of these fails, so Erlang, it has taken also into heart this on Antarctic surgeon philosophy. The process will not try to fix themselves. If any one of them shows the most minor weird behavior, it forces a failure. This is the Erlang let it fail philosophy, and it sends a signal to the supervisor in blue here, okay? And the supervisor has a supervisor bit set to 1 or true, which means that itself, it doesn't fail. Because otherwise, all the transitively linked processes will fail if one of them fails. So the whole thing fails, but not the supervisor. And this allows you to build a multi-level structure, which in Erlang is called supervisor trees. So the low-level supervisors are observing the workers directly, and then you may need also a higher level supervisor. So the AXD 301 switch actually uses this, and it actually has two levels. So there's the low-level supervisors and a root. And Joe Armstrong himself has assured me that he has never seen a system where you need more than that. Okay, I trust him on that. And then a final kind of also interesting system is the human respiratory system, which is here in 3 levels. So the breathing apparatus. So this is something that's programmed into every human. Okay, so how does the breathing apparatus work? So when the CO2 level in your blood reaches a particular threshold, this triggers something called the breathing reflex. And you breathe and you feel better, okay? But there's a second phenomenon that happens at short time scales when there's an obstruction in your airway, like you swallow a piece of chicken or something in your lungs, then your larynx, the connection to your lung will basically contract and close, so you can't breathe. So you feel like you're choking, and you feel very bad. Oh no, I'm choking. But no, that's actually a good thing. That means it's protecting you from things going into your lungs, and it's always temporary. The laryngospasm will go away after a few seconds. So this is the low-level automatic mechanism, but you can override the breathing reflex through conscious control. So if you're in a car, you drive into a lake or something, well, you want to hold your breath, and you do that consciously, okay? And you have the full power of your brain. 100 billion neurons are there to solve you, keep you alive, and so you hold your breath. Okay, so that's the second level, and it takes control when the first level, if it would not, you would drown, okay? But what happens if you try to hold your breath too long? Okay, I'm going to hold my breath until you give me that piece of chocolate cake, okay? Well, 2 things will happen. You will not die. Either you will reach what's called the breath hold threshold, and you will be forced to breathe. You cannot, so the breathing apparatus, so it's a fail-safe. If you're underwater, you're screwed because you will drown when that happens, okay? So the point is that by then, hopefully you're out of the water. So another point is there's the oxygen threshold. So if you're a trained athlete, you can hold your breath until you fall unconscious, okay? You will not be forced to breathe again. You will actually fall unconscious when the oxygen level in your blood falls. So that's the ultimate fail-safe. Once you fall unconscious, the conscious control just vanishes, and you start breathing normally again as an unconscious person, okay? So that's the ultimate fail-safe. So this is how the human breathing apparatus works. So this was deduced by me reading the Wikipedia ending on drowning, okay? So this is, doctors have determined this. So you can see it's a 3-level system, okay? And there may be higher levels like maybe you shouldn't make highways right next to lakes or stuff like that. So there's other levels, maybe long-term planning society that I won't talk about. Okay.
There's also evolution.
Evolution is the ultimate high level over millions of years. Yeah. So this was designed by evolution, but if there's problems, they will eventually be corrected, right? Takes a long time. Very long time scale. Yes, indeed. Okay, so some design rules. So each level has its own QTA. You have a breach detection. So one of the points is, when do you go from one level to the next? So by default, each level tries to solve its own problems unless that is not possible. Yes, Neil.
So one of the things that we've done is by working out residual failure rates, right? Sometimes the failure rate at a particular level is so low that it's not worth writing the code to mitigate.
There you go.
So literally, you say, this is 1 in 10 to the minor.
Why even write code for that?
Why just propagate?
Absolutely.
Which basically makes the design simpler. And
Absolutely. So you don't write the code, And in that rare case, you fail and the higher level takes over, and that's it.
But only is propagated.
Well, that's the point. How about, you can make the decision that the correct action is. It depends, right? Sometimes even ignoring is the right action, but after, perhaps at the next level up. Right, should we restart the dance? Yeah. We do that in the distribution. We have various levels. Sorry.
Okay, no, we're good. So there's also a time scale thing. So maybe if the solving the problem is at a completely different kind of abstraction level and time scale, why complexify this very simple lowest level by doing that? It should be then at the next level, okay? And then there's the notion of breach detection. How do you detect when you break? So you need to have some kind of an observation of the divergence between the desired and the observed behavior. So at some point, you will trigger a breach detection, and then you can do something like using hysteresis, because there is some issue that you don't want. You want to clean. You don't want to oscillate. A clean breach detection. Okay, and also correlation. So basically, here I have 4 levels at different time scales. So here, basically, I explain internal correlations and external correlations. So when you have these correlations, the point is that the probabilistic assumptions break down. The fact that you have exponentially distributed packets coming in doesn't work anymore. You have a huge amount of packets dumped in right away, very quickly. Okay, you can't really say they're independent, huh?
Either your supply fixed functionalities, or your going downwards, or your demand fixed set functionalities. And actually, you can reason about this, right? So, for example, the data diffusion system in Cardano, the credible worst case design is for 1/3 of the world's function.
Oof.
1/3
because of Carrington.
was a carrying.
It would only be 1/3.
Coronal mass ejection is the other phrase for it.
Oh wow!
Right? By the way, there's 50-50 chance of one happening in that. Right? That's one of the things. But only 1/3 of the world will be affected, because that's it affects
It's the side of the world facing the sun at the time.
Yeah, but it lasts more than 8 hours, huh?
No, they last.
And the one in the 19th century was over several days.
Right, okay.
So the world has a chance to turn.
Normal accidents.
But anyway, so what we're
You'd
saying
enjoy
is
it, Neil.
Living with high-risk technologies, yes.
we basically you design for credible worst case events, right? The point was, if everything else has failed, of course, if you're the last thing to fail, society's going to forgive you. Society. Sorry.
Okay, sure, no problem.
Give an example of internal correlations
Yeah.
we encountered. So in a network operator, usually they had a very complicated network design with lots of levels of firewalls and so on. And it was, and they were having terrible performance problems. When we looked into it in more detail, we discovered that these firewalls were actually not separate physical devices, they were virtual firewalls, and they were all running on the same platform. So what happened was, a packet would arrive, it would be processed by the first firewall, it would go out to the interface, and it would come back into the same device. And the process would go out of an interface, and back to the same device. 6 times.
Ooh.
So every arriving packet caused a burst of load.
Wow.
Right?
Right? That's how it caused an internal correlation.
Okay, nice example.
Designed it.
So what was it?
Yeah.
Yeah, they do it because it's the cheapest solution. And the manufacturer said it could deal with this rate. But the manufacturer's rate
Was for a single pass.
the manufacturer's rate is sealed, and the uniform will pass on the rivals. It didn't deceive first.
First, you had a factor of 6 immediately.
Yes.
So a load of 1 would be a load of 6.
Yes. That's why they've done the multiplying factor. So they haven't overloaded it on average. But what they haven't, but what they have to do it. The fact that, each packet was 6.
Firstly, yeah.
Okay. Okay, so the final point I want to make is something about time scales. So typically these different levels are happening at different time scales. We have the base system. I talk again a little bit about the rules, but once you go above that, the time scale typically increases. So when you have single packet level here, task level, for example, stop admitting new tasks, so seconds, configuration level, reconfigure, so this could be hours or days, admission data center elasticity, so that takes time. Software rejuvenation, so basically rebooting the system, a human in the loop. And then the final level is when you actually need to actually change the system. So that's a very low. So I mentioned the Carrington events here.
This is
Super volcano eruption.
whatever, yeah, but basically, ring of fire, cutting stuff out, whatever. Just causing people to think about different timescales stops them trying to mitigate character in the hardware.
In the hardware, what a place. Come on.
No, I've seen I see this, right? You see that people worry about things, and engineer, you've got to give them context about how much.
Sure. Context. Okay. So now I'm reached the end of the tutorial. So let me give a few conclusions. So I'll talk about advantages and limitations. So advantages, partially specified designs, both top down, bottom up. You can check feasibility. You can predict latency and throughput, so saving time and money. It doesn't talk about system state, doesn't assume anything, and it's a stochastic approach. This seems to be kind of a sweet spot. So it has a lot of information, but not too much. And it has the right default. So it assumes independence and you add dependence when you need it, okay? So dependence will not break it. You will have to just add a little bit, okay? So you have the three parts of the design: independence, coupling, and the multi-level management. But then some limitations. So of course you need valid inputs. You have to know something about your components. You have to know something about your couplings. It's not magic, You have to know what kind of hazards would appear. The other thing is you need systems with independent actions. If by default the actions are very dependent, like a user writing a text in Microsoft Word, it's mostly dependent actions from beginning to end, okay? So that is really not what ΔQSD is made for. That you can use some other way of looking at the system. And the third point is you need to do some computation. You need to do convolution, deconvolution, and other kinds of operations on these CDFs. So that can be significant, but it's reasonable, actually. It's much less computation, for example, than simulation, and even deconvolution. I mean, a current today laptop should be, touching on wood, powerful enough, okay? So basically, it's suitable as a foundation for a software design tool. Okay, that's what we're working on. So that leads to my final slide. So I've introduced ΔQSD, some practical experience, shared timescales, but still ongoing work. So we are still taking the experience of P&Sol and piece by piece, turning it into a well-documented and explained methodology. There are other slide decks and documentation, but maybe not really organized for dissemination. So these are mostly organized as presenting different aspects. And we do have an ongoing project, and we are looking for help like PhD students. So we have two main publications. So Mind Your Outcomes in Computers, and then a submission from January. So this is a big thing. This is all the algebraic reasoning. So this actually is a major result, and it has a big example here. And it has an example that I did not present, which is how you handle retries in caches. Okay, so that's the end. Thank you. The audience is wildly enthusiastic. Yes.
The audience is wild.
Wild and enthusiastic, but maybe